Thank you very much. And so again, hello everybody. I'm Dustin Whittle, and I'm a developer advocate who works on Uber's developer platform, where I help third-party developers and our partners build moving experiences. And so I wanted to talk a little bit about the couple of ways we use JavaScript across our engineering orgs. I think in order to properly tell the story, you need to understand a little bit about the scale and the environment in which we grew, and then I'll talk about how we build back-end microservices with JavaScript, how we build our front-end web properties, how we visualize data to understand cities better, and then how we expose an external API for the developer platform. And so again, as a matter of housekeeping, please ask questions through the app. I'm saving some time at the end to go through all of them, so please feel free, and your feedback is very much appreciated, so please be relentless and give as much feedback as possible. And so you probably know Uber by now. Push a button, get a ride. And so Uber's mission is really to make transportation as reliable as running water everywhere and for everyone. And in just 8 years, we've done that. We're actually one of the fastest growing companies that's ever existed, and we're on 6 continents and 73 countries, and then more than 470 cities. And we've done that by partnering with more than 1.5 million active driver partners who on daily deliver more than 5 million trips. And we did this in under 8 years, and last July we completed our 2 billionth trip. And so if you'll indulge me for just a second, we can take a little bit of a look at the evolution of the Uber app, because really this has been powered by JavaScript underneath. So if you travel back to 2009, this is pretty much what the Uber app looked like. You had a map and you had a button that said, pick me up. Pretty straightforward, pretty bare bones. And then in 2012, we released another version of the app that added more features like location search, ETAs, estimates, and the ability to select different products like Uber Pool, UberX, UberLux, et cetera, at the bottom. And then last year, we released a new version, and we refreshed it to add scheduled rides, accelerators for known locations, so you can have one-tap rides, and then an interactive feed, just to name a few. But as you can see, the Uber app has evolved over time, just as the company and the engineering organization has evolved as well. And so today, you can actually take an Uber ride experience. Along the way, you can play your music with Pandora, you can see local recommendations with Foursquare, and you can even order food with Uber Eats, and much more directly from the Uber app. But it's not just rides and cars. It's been choppers and boats too, from kittens to ice cream to even Christmas trees. We're not just moving people, but we're moving things as well. And the Uber experience is iterated in many ways. And this is really a coming-of-age story about JavaScript, so I'll talk a little bit about how we got there. And so this is a visualization of New Year's Eve from 2013 to 2017. And so if you just look at this is Singapore on New Year's Eve from 2013 to 2017 every year. And so you can see the scale of the growth year over year. And in June 2010, we launched our first ride in San Francisco. And by May 2012, we hit 1 million rides worldwide. And we hit 1 billion rides by February 2015. And today we exist in more than 73 countries. And so just if you look at the scale and the timeline of this, it's really quite fast. And to understand why we use JavaScript in certain ways and how we've iterated on it, you need to understand the scale of the growth. And so we hired a lot of engineers. They wrote a lot of software. And the reality is when you're working at a hyper-growth engineering company like Uber, it pretty much looks like this image. You're moving super fast. Every week we're launching new cities. Millions of people are using our systems in real time, and we can't simply stop our systems even for a minute for 1 minute of maintenance. It's nearly like changing the wheels on a car driving 80 miles an hour. And so we are organized as programs and platform teams. And the easiest way to think about this is program teams are built on top of technology platforms. Our platform teams build the technology foundation on which program teams can build customer-facing products. But we're all product teams. It's just whether the customer is external or internal developers. And so we invest heavily in building these platforms that enable developers to iterate quickly. And so building a platform that interacts with the real world adds a whole other level of complexity and opportunity as well, because you can't really control what happens in the real world. The physical world's complexity is infinite, but we only have 64 bits and a 500 millisecond SLA. And so there's often things that we can't really see that go into the technology underneath. People use our technology to make money, to go where they need to go, and so there's no safe time to pause, which is why we prioritize availability and scalability over all else. And so in order to do this, we actually have 15,000 repositories that power more than the 3,400 microservices that we've released more than 260 of them back to the open source community. And you probably just know the Uber Rides app or the Uber Eats app. But we actually have more than 10 mobile applications and more than 250 web applications. And a large piece of the core technology behind this is JavaScript. And so Uber's ability to scale has come from high-velocity, hard engineering along with autonomous teams and domains. And so we design foundational services that are designed for high scale and durability, and we focus on developer abstractions that allow developers to be productive. And so we're a polyglot engineering organization, and we use a few languages in production. And so today we're moving towards Go and Java, but again, this is a coming-of-age story about JavaScript, so I'll talk about sort of how we evolved and got to this scale with JavaScript, and some of the reasons why we're migrating in other directions. And so we use Go, Java, Node.js, and Python in production today, and this is really in order of preference. But let's talk about how it really started. It started with the freedom of choice. When you're growing super fast, you're hiring many engineers, you want them to be as productive as possible, as fast as possible. They tend to hire their friends. Once you get popular in the open source world, you start to build a community around your projects, and so it becomes easier to hire people who are like-minded, come from your culture. And so originally, when we decided to use JavaScript, we realized that it was a single stack for the front end and the back end, and it made it very easy to iterate. And so again, it has a simple interface with thorough documentation that makes it quick to iterate and prototype. It's asynchronous, nimble, and flexible, so it allowed us to avoid concurrency challenges early on. And it also had an increasingly mature module ecosystem. But today, we only use Node.js for our web applications. And so why Node.js? Early on, like most great web companies, Uber started as a PHP and MySQL shop. It was actually contracted out with a bunch of comments in Spanish, and then at the time, Node.js came along. We were very early adopters of Node.js. In fact, we prototyped the first version on Node 0.2, and we were running Node in production at 0.4. And so it's come a long way since then. At one point, more money moved through the Uber's app and our Node.js app than any other Node or JavaScript app in the world. Until recently, PayPal has migrated to Node, so they've sort of surpassed us. But why Node? Node has a few core strengths that lend itself well for our use case. First, it handles asynchronous I/O with a non-blocking single-threaded event loop that's particularly well suited for building distributed services that make many network calls underneath. And Node.js and more JavaScript in general is excellent for quick iteration. And again, it's easy to prototype something and then to iterate on it with a large team. And then 3, it has a great module ecosystem. You don't have to build all the components yourself. There's already a large community there that you can build on top of. A talent pool to hire from, as well as existing modules for common use cases. And so throughout this talk, we'll talk about 4 ways in which we're using JavaScript today. On our marketplace platform to provide the core services underneath, again, we have an architecture that consists of more than 3,400 microservices. 100 of those pertain to the core trip flow. So just pushing a button and getting a ride from A to B is 100 services talking underneath. And then we'll talk a little bit about our web platform and how we build front-end properties with React and Express, and then how we better understand cities by visualizing data. And then finally talking about how anyone can build applications through our developer platform. But Uber invests heavily in developer productivity, and so we've invested in a bunch of different things, in a bunch of different platform teams that make it easy for developers to be successful from their first day at Uber. And so it really starts with the core infrastructure. This is our compute, network storage, our cloud environments, our on-prem environments, and it abstracts this away so that developers can focus on making magic. And then we have our developer experience team. This is really focused on the developer toolchain. So how easy is it to build an app and deploy to production? And then as you add dependencies, as you need to interact with other services, we have our marketplace platform. This is the single gateway to all the 3,400 microservices underneath. And then on top of that, we have our external components. We have a web platform team that maintains a performant and secure, reliable web foundation. We have our mobile platform team that's focused on enabling thousands of mobile developers to build world-class performant applications. And then we have our developer platform team that focuses on exposing all this functionality to the outside world. And so we have this cultural value to let builders build, and this really means to not block people and to give them the tools they need to be successful. And so when you want to launch a new service, in this case a JavaScript microservice at Uber, you send a proposal with a request for comments to the entire engineering org that gives you a basic outline of what you want to build, the timeline associated with it, any security concerns, and any operational concerns. And then you start with scaffolding that is purpose-built around our stack. So we solve a ton of problems for you, and if you use we want to make our tools so good that you'd be foolish to use any other tool. And so by building the best possible tools, you get the widest adoption because it's the easiest, it allows you to be the most productive. And then you deploy with standardized infrastructure. And so we use playbooks to operationalize our teams at scale, and I'll talk a little bit about this later. But if you think about what it takes to build a web application that's user-facing today, a lot of this is more than just the JavaScript interface. It's how do you handle assets and edge cache? How do you handle communications internally, whether that's through HTTP or Thrift, T-channel, whatever. How do you manage translations, internationalization, data, network, compute, storage? The list goes on. And so I'm not going to talk about any of that today. I'm going to talk about how we build on top of it. And so our marketplace platform at its core is pretty straightforward. We have a iOS and Android application that talks to an HTTP endpoint or a series of HTTP endpoints that talk to underlying services. And at a really high level, the services look like this. You have supply, you have demand, you have authentication, the ability to match supply and demand, pricing, etc. But realistically, it looks a lot like this. Again, we have more than 3,400 microservices that build the Uber's engineering. That's right. And so this is one of the things I'll talk about shortly, which is how do you figure out which service does what when it's this complicated? How do you get visibility into performance problems in distributed applications? And so again, our marketplace API is really the single API that external applications talk to, and it acts as the gateway to the more than 3,400 underlying microservices. And so we expose over 1,000 HTTP endpoints that make it easy for third parties, for our program teams to build on top of. But also it's a single place for monitoring and documentation to make it easy to discover services and understand how to use them. And so ultimately, the marketplace gateway is really just an advanced traveling salesman problem. It's a logistics problem. How do you match supply and demand? How do you make it an efficient marketplace? How do you maximize the number of trips, but also minimize the wait times for riders and for drivers? And so if you think about Uber Pool running in a city, it's a complex traveling salesman problem. And so I'll dive into some specifics about how we scaled with Node in just a second, but to understand this, take a look at our timeline. In 2009, we started with PHP and MySQL. Around this time, 2010 is when Node came out and started to get popular adoption. We started to move towards Node.js. MongoDB at the time is web scale, and it turns out that's not really true. So we migrated to it and then away from it. We started to replace it with things like Redis. We started to migrate to MySQL because we were originally on Postgres, and we sort of maxed out our write throughput on Postgres at the time. And then we started to write our own data store, which is schemaless, built on top of MySQL. And then, as of recently, there's been a large push to sort of standardize on Go and Java. But let's talk about how we got here from JavaScript. So monoliths aren't necessarily bad. Well, they're not bad at first, but they quickly turn into a ball of mud. And so monoliths really optimize for developer velocity of early stage projects when a single team owns it and it consolidates all your operational overhead into a single place. There's only one application to deploy, one code base to maintain. But microservices are a thing. But microservices are really just a thing that's focused on only one thing. But one thing doesn't mean one API, it means one business domain. And so as we started to break apart our monolith and create many microservices, we learned a few things along the way. One, it gives clear ownership boundaries. If there's a single team that owns a single business domain, you can map that to individual services. There's one team that owns authentication and identity, so they own the authentication identity services most of the time. It also gave us product-specific velocity. Again, when you're growing super fast and you're hiring all these new engineers, where the average engineer is less than 6 months at the company, you really want to make it very easy for them to move at their own pace. You don't want legacy foundational services blocking the product development of a new product. And so it allows us to move the business faster. And it gives teams independent velocity. But it also solves scaling issues, not only internal systems, but also the company. How do you group people together? And then it gives us the ability to consolidate training documentation and our tooling underneath. But ultimately, it gave the teams language and platform independence. And this is a large part about how we started to adopt Node. It wasn't some mandate that came down from some executive team. It was literally engineers like JavaScript. Node seemed mature enough to solve the problem at the time. We had a bunch of talent that was familiar with JavaScript in the Node ecosystem, and so the team just sort of organically grew from there. But as the team goes from hundreds to thousands to multiple thousands, you really need to start to standardize. And so that's really what we started to do, is say, okay, we have a preferred set of languages, but you can use any tool you want for the job. But it also gave us reliability of the system as a whole. Each service is independent, each service is scalable, and each service is independently testable. But there's some bad that comes with the good. One, it's increased complexity. To your point, when you're looking at a high-level version of it, it looks like spaghetti. So how do you do discovery when you have this many services? How do you name them? Early on, engineers are creative people. They tend to name things interesting. They give things interesting names, and they don't ever have anything to do with the service. So the authentication service isn't called the authentication service. It's something very different. And so how do you map that to the stuff underneath? You need to be able to do discovery much more consistently. Eventual consistency becomes a problem. Eventual consistency ultimately becomes a problem because your data no longer lives in a single place. It's spread out across many databases, across many services. And then distributed tracing. When you start to run into performance problems, how do you figure out the root cause of the performance problem? And so we built some tools to help alleviate some of these issues. And then obviously there's the operational overhead. For every service, you need to monitor it, you need to deploy it, you need to instrument it, and you need to make sure it's secure. And so every time you add a new service, if you're doing this with independent tools, you start to have to duplicate all this operational overhead. And the last thing is it ends up being with repeated code and repeated effort. And so when you have many teams, how do you make sure that there's not multiple teams and an engineering org of thousands of people building the same types of services? And so Martin Fowler has this great graph that shows for less complex systems, the extra effort required to use a microservice architecture outweighs its benefits. But once the problem becomes more complex and the team size increases, the benefits outweigh the risk. And so choosing a microservice architecture largely depends on the complexity of your application, the complexity of your team. There is no golden rule. And so one of the ways that we ended up scaling our Node applications was by solving a few different problems. One, how do you do application level sharding? We used to use Google's S2 library to shard the entire world. So the Google's S2 library basically takes a sphere and breaks it down into different regions. And so from those regions, we can start to shard our database, our applications, based on geographies around the world. And so the problem with this is when you're scaling applications that do real-time requests that are specific to a geolocation, you have surges in demand. Something like in New York City, the peak demand is not going to be the same as in Amsterdam or in Singapore or in San Francisco. So how do you shard that environment? And so one of the first tools that we wrote in Node.js to help us scale applications was RingPop. RingPop provides application-level sharding. And so it allows you to bring distributed cooperation coordination to distributed services. But really, it's a hash ring on top of a membership protocol that allows you to choose either this instance of our application can handle the request, or I need to forward it to the appropriate instance that can. And so it looks a lot like this. For every node instance you run a RingPop client, and this RingPop client can understand which requests this instance can service. So I can handle requests for this particular location or for this particular service. And so this allowed us to easily decide how we wanted to shard the backend, but manage it all at the application level. And so RingPop is written in Node.js, and we have clients for a variety of languages. One of the next things we learned is that making requests in HTTP was really built for a world in which you're connecting from a browser, a client, to a server. But when you're making server-to-server requests, HTTP is expensive. And so there's a more efficient way to communicate between these back-end microservices. And so at the time, Thrift existed from Facebook, but it didn't have the language support that we needed at the time. And so we wrote T-Channel. And so T-Channel was a RPC protocol that allows us to make very efficient requests to the back-end services. And so T-Channel is available in multiple languages, but this is how we actually communicate in our underlying microservice architecture. And then one of the last tools that we built for Node.js was Jaeger. And so Jaeger was originally built on Twitter's Zipkin, and it provides distributed transaction tracing for complex distributed apps. And so when you're looking at a complex application, you want to figure out where the performance problem is. You want to have visibility into the underlying calls so you can start to see where the hotspots and the root cause of performance problems lie. And so a large part of what we did was figure out how to bring observability to our distributed services. And so we did that through a few different ways. By instrumenting T-Channel, by using Jaeger to visualize, and Jaeger client to instrument the underlying services. And we scaled out our Node applications using RingPop. And so there's great engineering write-ups on our engineering blog about each one of these services. I don't have too much time, and there's a lot of content, but I'll follow up with the slides at the end. And so ultimately, Node is just a thin wrapper around C++. It's a thin scripting layer around C++. And so all the Linux performance tools you're used to just work. And so Uber is also built on top of those. So whether it's using Node, building Node CPU flame graphs with ptrace, you can still just use all the normal performance tools you'd like to figure out performance problems in your applications. And so the reason I like to point this out is that you should learn how to profile applications on Linux, and then you should figure out how you can get visibility into those distributed applications. There is no silver bullet. And so we learned a couple of different lessons. And when we started with Node, performance wasn't as big of a concern as it is today, but since we've migrated to we started migrating all of our core services, we realized that the latency is too high for ultra-performant backend systems. Again, we adopted earlier versions of Node, so a lot of this has changed in time. But when you have dynamic typing, dynamic garbage collection, all of a sudden the performance isn't as predictable as it is with other languages. And so the P99 for max latency started to become a problem. It wasn't about the average latency for the request, it was about that one request that takes a lot of time. And so early on, it made it very quick to iterate, but as the size of the team scaled, the developer velocity started to slow down. And a team of 5 people, it's very easy to develop, but as you add 100 or even 500 committing to the same code base, things start to break down. Again, using microservices gives us flexibility and makes everything independent, but it also requires you to have a tight interface between the different services. So if you rename a field in one place, now all of its dependencies need to adopt that. And so, again, microservices require a tight interface, and by using languages that support static typing, you're able to enforce that much earlier in the process. And so when you have large development teams contributing, this starts to really have an impact at over 100 developers. And so it allowed us to catch issues at build time rather than at runtime. And again, hiring. It was quick to learn, but it was easy to write poor quality code. It allows you to move fast, but it also allows you to be sloppy in the process. And so one of the nice things is that you can write performant, high-quality JavaScript code, but that takes experience. And when you're hiring people very quickly, even when they're amazing, sharp people, if they didn't learn Node and they don't know the pitfalls of common design patterns with Node, they're focused on getting stuff done. And so you want to make it safe for developers to build things quickly, and Node.js sometimes allowed people to be sloppy. How many people remember the library that took down the internet because somebody got annoyed that somebody wanted to rename their package? So there's a great ecosystem of small libraries in Node.js, but there are some issues that go with that. A lot of them were immature compared to their Java or Go counterparts. A good example of this is the Node HTTP client. And so the Go version is 10 times faster, but it's purely the implementation. If it was written in C++, it would be much better implemented. And so while you have this great ecosystem of small libraries, sometimes the libraries are too small. Sometimes the dependency chain isn't necessarily clear. And so you have issues where left pad can take down the internet. And then ultimately, don't be afraid of writing C++. So also, again, it's just a small scripting layer. So sometimes when you need more performance, the right thing to do is just go a level down and then write bindings that expose that functionality to your language. And I think oftentimes people don't necessarily think they should do that. But there's nothing wrong with that. And parts of our core services are written that way. And so, again, just to recap some of the lessons that we learned, HTTP and JSON was designed for browsers. Using RPC with T-channel and Thrift is much better for computer-to-computer requests. When you're just microservices communicating between each other, it's much more efficient to talk via binary wire protocol. This one comes down to scaling with large teams. After a certain age, microservices should become immutable. At some point, it's easier to ask people to move to a new service than it is to ask them to change all the interfaces that connect to that service. And so we have this idea that after a period of time, a service can't change, that we will release a new service that replaces that functionality. And having multiple language allows for team preferences, but it also starts to segregate developers based on their culture. And it starts to eliminate the ease of use of reusing code, reusing people on teams, allowing teams to move around the company. And so this led to some issues. We'll just adjust that for everybody. Performance problems are difficult to debug when you have these complex distributed applications with thousands of services, so we had to invest heavily in standardized dashboards that give you meaningful information and observability tools that allow you to get to the root cause of these performance problems, like with Jaeger. And logging should never slow down production. If anything, logging should be dropped rather than delay the next request. But all of these decisions are architecture decisions that are just trade-offs. It's easy when you're growing very fast to go with to let the momentum carry you, but oftentimes you need to step back and be intentional with these decisions. And so a lot of these lessons come because nobody stepped back and made intentional decisions. Engineers just built things to survive, to be able to scale so things weren't falling over. And so I think that's a salient point. And so the next way we use JavaScript is really with our web platform. Our web platform today is based on React and Express and a bunch of open source tools, but you've probably seen the various properties, whether it's Uber.com and checking out for a ride, if you're interested in self-driving cars, our advanced technologies group, Uber Freight to book a load and tap a button and book a load, signing up to ride, getting estimates, ordering food, moving packages or things around town, managing your business, visualizing data for city governments, and my favorite website that we personally maintain is developer.uber.com, where we empower third parties to build moving experiences. But the reason I show all of those is we have more than 250 web applications that we have to maintain, and without a consistent foundation, all of these applications would have been built off entirely different tools and different architectures, which creates a higher likelihood that they're going to have problems, whether that's security vulnerability, or just duplicated effort across teams, which you start to realize investing in platforms solves these problems. And so you'll notice the theme is that we invest in these technology platforms that allows developers to use a standardized stack that's purpose-built for our tools. And so let's talk a little bit about how we did that for our web platform. So at a high level, our web platform is built on Node.js and NPM, like all good JavaScript applications. And we use Express as it's a lightweight framework that we've extended with a bunch of middlewares. And on the client side, we use React and Redux, pretty straightforward. None of this is particularly cutting edge. I think this is a pretty standard open source stack these days. And so we use Nginx and Hot Proxy for our front-end web servers and load balancers. We use NPM to manage our packages. Babel so that we can use the latest generation of JavaScript. Express so we have a lightweight web framework. React for UI rendering. Redux for state management. And then a bunch of tools that are built on top of Gulp that allow us to have a consistent build and deploy pipeline and standardized build tooling across all of these applications. And so for the most part, most of these applications are built using the same stack. And it comes with some other special sauce that we need to add on top that makes it purpose-built for our stack. One, we need an internal NPM registry for private package management and then caching and basically better resiliency so we don't get blocked by deploy issues. When you have a large team, you want to make it very easy to scaffold new projects. So we have our own equivalent to VOman that allows us to bootstrap new applications with these best practices built in. I don't want to have to spend a day configuring Express to use all these middlewares. I just want to create a new project that's ready to go. And then we customized customized Express with a bunch of middlewares that allow us to handle standardized authentication, handle security issues like XSS, cross-site request forgeries, and content security policy on the front end, without it having to be a lot of work. It should be baked in by default. And then handling metrics, logging, internationalization, errors, instrumentation, analytics should just be something you get by building on top of our framework. And so our framework not only uses Express, but we extend Express to be built around all our internal tools. The libraries we use for translations, the libraries we use for our analytics pipeline, et cetera. And that's on the server side, but we have the same thing on the client side. So if you want to quickly build applications, you want a UI component library that makes it easy to build drag and drop components. And so we built the library on top of React.js. And then again, we don't use HTTP for everything, so we have our own RPC library on the client side that allows us to intelligently use HTTP or T-channel or whatever way your service is actually communicating. And then finally, shared build tooling powered by Gulp that allows us to have hot reloading, use the latest versions of JavaScript, and then make it easy to deploy assets and deploy our applications. And do it in a consistent way with standardized testing and standardized code styles through Lint. And then universal rendering for the server and client. I think this is, again, one of the biggest reasons we continue to use Node.js today is it allows us to write the same code on the client side as the server side and allows us to use isomorphic rendering to provide the same views, whether it's front end or back end. But we go a step further than that, and not just in exposing a front-end client that's written in React, and a back-end service that's written in Node.js. We actually separate our front-end services, those that serve the web pages, or at least the shells of the pages, from our back-end services, those that interface with the underlying microservices and provide data to those views. And so there's a couple of different reasons for this. One, the services could take advantage of the universal rendering and tooling, so everything just works out of the box. But you can also better utilize languages for a specific use case. So if you want to implement certain services in Go in the back end, you can do that, and then you can just talk to them via Node and expose that in JavaScript on the front end. But it also allows you to deploy and scale your services separately. And finally, you can reuse those back-end services for more things, like a mobile client or for our external API. And so if you take a look at what our architecture looks like, I had to adjust this to make some people happy. But at a high level, this is what the architecture looks like. In the client side, again, it's a React application. Inside of that, we have a set of standardized React components, and then we use Redux for state management along the way. We have our own RPC library underneath that handles talking to these backend services. And then we have our backend application server, which is just a proxy from Nginx and Hot Proxy. And then we have our application server. The application server has a static assets pipeline that really just offloads things to a CDN. We have a way to route requests to the underlying backend services, and then we have the actual pages that get served to the browser. And then along there, we also have ways to do isomorphic rendering, as well as a way to have a shared routing mechanism between the front end and the back end as well with React Router. And then, so one of the things that we focus on is these React components to make it easy to have standardized UIs without having to write all the code yourself. So most people are familiar with Bootstrap or Zerb's Foundation. This is our equivalent built on top of React. And so we liked it because it allows us to, if you saw all those websites, I personally think they all look very good. And that's not because they had a dedicated designer on each team who made everything pixel perfect. It's because they had this standardized tooling that made it look good out of the box. And so that's one of the reasons that we have these React components. They're really optimized for performance, and they encapsulate the style so that over the wire they're as light as possible. But they also have analytics and instrumentation baked in. If I click on a form element, I don't want it to track the Redux, the state, and when they type in some data and pass that along, I want to be able to intercept those events and have them automatically pass to our analytics pipeline. And so by having all this stuff built into the front end, it just makes it easy to do out of the box. And then as brands change over time, which they eventually do, it makes it easy to get seamless upgrades to new versions. And so we believe heavily in writing CSS and JavaScript, and this is for a few reasons. One is because it's ultra performant. You can only ever serve the CSS that's actually being used on the page, and you don't have to handle it at runtime. And so we try to, we use one of the engineers on our web platform team who actually wrote Styletron outside of Uber, and then we adopted it on our team as well, and we started to use it internally. So all of our CSS is powered by Styletron and the latest generation of our web platform. And this makes it easy to manage all styles in one place. You have one file, one React component, one thing to edit. You don't have to track libraries across libraries to figure out how to make something look different. And so one of my favorite ways that we use JavaScript is actually in data visualizations. And so this is one of the most powerful ways that we use JavaScript today. And so this is a day in the life of San Francisco. And so if you take a look at this visualization, this is actually powered by DeckGL, which is a WebGL framework we've released. And it allows us to understand how cities work. One of our cultural values is to celebrate cities. And what you start to understand is that every city is very unique. But in order to understand how it works, you need to be able to visualize it. And so we've invested heavily in these visualization frameworks that allow us to do that. And so you can check these out a little bit later, but I'll talk through them quickly now. We have React Viz. This is a charting library that basically maps to React components. And so if you're used to building excellent charts with D3, this is a React interface to do that with standardized components for various charts. Most of the maps that you see on our website and in our applications is powered by React Map.gl. And so if you know Mapbox's GL library, this is just a React interface to that. And then one of my favorite libraries is DeckGL, which allows you to use millions of data points and to visualize them in a high-performant way. And so really, it's built on top of WebGL 2, and it's a layered approach for visualizing data. And then we also have released LumaGL. And so LumaGL is a simple interface to WebGL, actually. Standard interface using ECMAScript 6 to WebGL 2 that also deals with some 64-bit precision. Okay, so React Viz, again, fancy charts, very easy through a React interface. You can check out more at JavaScript or uber.github.io/nodeweb. And so it gives you a composable visualization system, but really makes it easy to render charts, whether it's line, area, bar charts, heat maps, scatter plots, sunburst, and tree maps. And so every different chart and visualization you can imagine is supported by React Viz. And so some of the ways that we use this today are to, again, understanding how cities flow. And so what you're looking at is an interactive map of New York that as you mouse over, you can see the pickup and drop-off locations from a particular point. And so if you're a city manager trying to understand where supply needs to be in a city over time and where people go get dropped off, this makes it very easy to understand that information. This is another visualization that shows density in New York. And so this makes it easy to understand over time what do pickups and drop-offs look like in certain locations. And so again, all of these visualizations are powered by DeckGL, and DeckGL is really designed to make visualization of large data sets extremely simple. And so it's easy to visualize a couple thousand, 1,000 pieces of information. It's much more complex to visualize in real time, millions of pieces of information. And so using layering and instancing, we're able to provide high-performant visualizations like you've seen previously. And then LumaGL. LumaGL just makes it very easy to interact with WebGL. So it's a modern interface for dealing with WebGL, and it's a component-based platform that handles 64-bit precision, which we need for the degree of mapping that we do. And it also provides a better way to handle errors in WebGL. And so you can check out more at deck.gl. One of the best examples I think they have is when mapping yellow cabs versus green cabs over the course of the day. And so sadly, I don't think this animation's playing, but what you can see is Manhattan rendered in 3D, and then the traffic flows across the real cities all done in real time using millions of data points. And so this is actually quite an impressive feat to be able to do in JavaScript and have it be high performant. And so all this is available as open source, and we're completely open to pull requests from the community, so feel free to check it out and follow up. And again, this is one more visualization that shows over the period of 24 hours what drop-offs look like in San Francisco and the Bay Area. And so one of the biggest ways that we use JavaScript today is to, again, visualize cities so that we understand how to most efficiently work in a city. And most of this is powered via JavaScript, and all the libraries I've talked about today are all open source and available on uber.github.io. And so the last place that we use JavaScript is through our developer platform. And so we want third parties to be able to build moving experiences, whether it's offering on-demand rides or doing on-demand delivery. We expose all these 3,400 microservices as 4 business domain objects, and we make it very easy to interact with them via our Node SDK, so that if you want to be able to offer on-demand rides inside of your applications, or to be able to plug directly into the Uber trip to create a custom experience, you can very easily do that through our Node SDK. And so again, almost all of this is powered by open source tools, and so we very heavily contribute back to the community, and not only the tools that we use and through our presence on GitHub, but also through our engineering blog. And so we write tons of tutorials that go very deep in how to use some of these tools and sort of why we built them. And so for a talk like this, I wanted to go very quick at a high level through many of the tools, but the best way to follow up is through the deep dives that live in our engineering blog. And so if you're interested in some of the Node backend tools, you can go to github.com/ubernode. And so this is really focused on all the open source backend tools to build Node.js applications, the things I talked about earlier, things like ringpop and Jaeger and T-channel. And then you can go to github.com/uberweb for some of our web front-end property, web tools, like our standardized lint rules for having consistent code, and then all the other sort of visualizations that you have. And then again, finally, is our Uber engineering blog, eng.uber.com. We dive into all of these tools and through in-depth write-ups. So the best place, I think, for every tool that I've mentioned, we have blogs that go very deep into them. So I think that's a great place to dive in. And so we want to build an open platform for building moving experiences, not only using our tools, but also by providing the data that we use to build a great service, and we want to expose that for third parties. And so what future will you build? All of these tools, all of this talk is built from people way smarter than myself. I just get to be the person that represents it. But this comes from thousands of engineers working on all of these tools. And so a lot of the credit for this talk goes to the many smart people at Uber. And if you want to join the team, we have offices in Amsterdam and San Francisco, around the world. So feel free to follow up. And there's some great talks that I also recommend as well. And with that, I would like to open it up for questions.